Good afternoon, statisticians. This is Dr. Schulman. There's something on my shirt. I'm going to make you the video for regressions 10.2. It goes right along with correlations. Basically, the regression is that line we're trying to find within the scatter plot. So if it's still kind of tough for you, let me know. But I'm gonna just go through the book and the video. I'm not gonna do like a little intro where I explain stuff because I feel like I did that already. Maybe I will. Maybe I'll do just a little bit. So I'm sharing my screen right now. Um, I am here in Intro to Stats. We've done so many videos already. Hope you're not too bored yet. But here's regressions and what they are. Now, there's not a lot of problems here, but basically the regression. I know I've shown this before. If this is, remember, this is our predictor variable or our x. This is our outcome variable, our y. These are all the dots. So this would be, sorry, just want to get rid of the top so you can see it. Let's say this is a pretty strong positive correlation. And what do we want? We want the regression line. That's the line we're trying to find. Basically, it's like the least squares. We're trying to find the least squares. It's figuring out all of these differences, and it's basically making a line of best fit. That's all that's happening here for a regression. I'm sure it'll be some more stuff in the book. Remember, we can do this on Excel, which you will have access to, or you can do this on StatCrunch. I'll show these again, but basically this is where stuff gets a little tricky because we're actually doing some equation. These are used mostly for observational studies because we can't manipulate stuff. We're just trying to find the relationship. So try to remember when it says the word correlation, it's not something that's caused. We're looking for the relationship between these two things. That's what it means. We're trying to find the relationship. Now, our null hypothesis for these things, our null would just be that there's no relationship. Our R is pretty much zero. I know, frown face. And remember, our R squared is going to be what? How much of Y is predicted by the relationship of X and Y. Hopefully that stuff's helpful. And then our HA or alternative hypothesis just means our R is significant. Our R value is significant. That's all we got to find. Okay. We use stuff like critical values to find it. If we didn't have like statistical like programs to help us, but this is just how that it works. So we're gonna get to 10.2. I'm gonna open the book, I'll look through it, then I'll try these problems with you guys virtually, So I'm gonna go to modules. Sorry, I'm gonna go to my math lab and mastery. And I'm gonna open it up. And thanks for the feedback on the videos. If there's stuff you want to see different, or if there's other stuff you want me to show, just let me know. People are doing pretty good. People are doing pretty good. So let's go to, when I'm in here, I go to e-text, e-text right here. So the whole book's opened up, and I just want to go to 10.2 and see what the book has in store for us before I try the problems. Here's 10. Here's the 10.2. Oh, cool. Well, we're not going to go right to the problems. They want to know what a residual is. Okay, so yeah, let's figure out exactly what that means. We've got equations. So let's figure out everything they want us to know about this. Okay, so we just have to go one back to 10-2, which is regression. Okay, so some cases the two variables are related in a deterministic way, which one variable is exactly determined without error. This is if there's no error. Okay. We're converting the difference between inches to centimeters. But such equations considered in algebra course, but statistics course is for on probabilistic values. So there is always going to be a little bit of error. For example, the height of a child cannot be determined completely by the height of the mother. And we got Sir Francis Galton who studied that. So as usual, no matter who they tell us about, I'm going to show you a picture of this human, tell you a little bit more about Galton. Oh, that was long. Here's our friend Sir Francis Galton. We're talking 1822 to 1911. That's interesting. He did 340 papers and books. He developed the concept of correlation, which was widely promoted as the regression towards the mean. He was the first to study human difference and inheritance of intelligence using questionnaires. That's really cool. So he did this to figure out psychology, how much we could pass on things. I really think that's interesting. He was a child prodigy. He was reading by the age of 2. At 5, he knew some Greek, Latin, long division. By 6, he moved on adult books like Shakespeare. At 6, ooh. So at 16, yeah, he's very bright, a very bright human. Nervous breakdown. He elected to take a poll pass B.A. degree like his half cousin Charles Darwin. Oh, that's fun. He's related to Darwin. Meteorology, polymath. Okay. So if you want to look more about him, I think that's really interesting to see why he came up with this stuff. But his whole idea was the inheritance of abilities. That's what it looks like. Interesting stuff. All right. Go to see. All right. So let's keep it going. So given a collection of paired sample data, the regression line or line of best fit or least squares line, they all mean the same thing, is best fits a scatter plot. And this is the equation. Okay, so let's do this. And I know I've written this before, but I'll have some notes on the side as I do this. Okay. So here's our equation. It's just like y equals mx plus b. In our case, it's y. This is our outcome variable equals m. That's kind of our slope. Oh, sorry. My bad. When I write it exactly, I have it. So I have BO plus B1x. So again, this is our outcome, the y, and this is our input variable. Now this is, you can think about as your y-intercept. In this one, this B1, we can think about as the slope. Okay, those are the parts. So the equation is a relationship between the x, the predictor variable, or the input, or the independent variable. I usually call it the predictor, and y, the outcome or the response variable. Where BO is the y-intercept and B1 is the slope. Cool. All right. So these are small for samples. This is, so we use the little ones for samples, and you use betas. So, okay, so BO is for sample and B1, and then BO will be the y-intercept for a population, and capital B1, that's beta. This is for when you're using populations. Remember, the only difference for the population for most of these formulas is the standard deviation. We haven't seen any difference in population yet. Now, this isn't predicted because we have the whole population. This is why you can consider like the actual values because we have everybody. XY is random sample of numerical data, quantitative. Shows a straight line pattern. We've got outliers. Like I have a strong effect. So for each value of x, the corresponding y have a normal distribution. The different values of x, the distributions of the corresponding y values all have the same standard deviation. So if the standard deviation is off, there's a problem here. And for different values of x, the corresponding means that they're along the line. Okay, so the methods of this section are not seriously affected for normal distributions and extremes. So here we go. So here's to find the slope, and here's to find the y-intercept. So what does this mean? So to get our slope, here's our first formula. Remember, this is for a sample. This is to find the slope of the regression line. It's r value sy over s of x. And then the y-intercept is going to be the mean of the y minus b1, which is the slope, times the mean of the x. The bars just mean the means of each. So don't freak out too much. What are the s's? Remember that whenever we have these s's, they're just going to stand for standard deviation. That's what that means. Now, this is it worked out with the standard deviations. If you didn't do the standard deviation beforehand, you could use these formulas, okay? But pretty much for each one of these, we're going to be okay if we just use our standard deviations and we use our mean. That's how we can get those values. What is the R? That's our correlational coefficient. So all of these we can figure out by going the long way and getting R first. Sorry, I didn't put correlational coefficient there. That's where this all comes from, okay? This is your correlational coefficient. Remember, each one of these things we can find by hand or from the computer like we did before. Notice that this is 3 significant digits, so 3 decimal places. So just really keep that in mind, which ones are 2 and which ones are 3. Okay. The next big thing is the error, but we'll get there. Using technology to find the regression equation. All right, these are a bunch of ways. Let's do with the Excel. Why don't we do the Excel first? So I'm going to use this data set with jackpot and tickets. And we can actually also do the standard deviation. We'll do it this way. We'll do all 3 ways to find the all the parts to this equation. So jackpots is 334, 127, 300, 227, 202, 180, 164, 145, 255. Then we have our tickets here, which is 54, 16, 41, 27, 23, 18, 18, 16, and 26. Okay, so the first thing I'm going to do is just have the computer automatically populate it. I'm going to highlight everything. I'm going to insert what? One of these dot plots, a scatter plot. First thing I want to do is just change this title because it's bad. It's jackpot to predict lotto ticket sales. So that's what we're trying to find. I'm going to put the titles in here. So this is the tickets sold. This is the jackpot amount. Awesome. So the one thing we can do is we can change this to like really spread it out to see it, but I try to leave zero when I can. The one thing we have to put is our trend line. Now, we go to more options on our trend line. We can put the equation and the R squared value. Once I put those two, it should tell me everything about it. If you want to make your line fancy, we can make it thicker. We can make it red. We can make it solid instead of dotted. We could add pieces to it. So it really looks like a line here, you know? That might like make it look prettier. So that's the line we're really trying to find. How'd they get this value? How'd they get this value? How'd they get this value? So I'm not going to show you all the steps, but I'll definitely use the little equations just to show you that we can figure this out kind of like manually. Sorry, I just have to move this. So I can figure this out kind of manually. So here's the formulas for B1, y-intercept, and all this stuff. So to get these formulas, what are some things I can do first? I can go to data and I can go to data analysis. I remember you have to like set that one up. And I can go to a correlation. I think there's one for regression too. We do one at a time. I'll do regression first. The input Y range is my tickets. The input X range is my jackpot. Oops, I messed it up. It should only go down to 10. And we have labels on the top. We're gonna put it on the same thing. Oops. Let's just put it here. I'm pretty sure that's how I could set it up for the output. Yes, that's where it's going to put all the outputs. So it's not on a different page. Residuals and things like that. Let me just click OK. I'm just adding some more pieces. Oh, sorry about that. So I'm just going to put on a new worksheet. Okay. I guess I hit help by accident. Oh, because I messed up my X range by something I did. That's all. If that ever happens, just look back at what you messed up. And I messed up my Y range. I think it's when I try to put the output range somewhere and messed it up. That's okay. We all make mistakes, right? So we already have our R and we're R square. We know our R square is 0.89747. We go back to sheet 1, 0.8975, whatever it is. We want to turn this back to R, right? We can say what R is. Then we could do equals square root, because we already have it. I'm just showing you other ways to get the values. 0.8975, and it should give us this 0.995 value. Perfect. We need the mean, so I'm just going to do X bar. I'm going to also do Y bar because we need both of them. So our X bar is what? This value. It's just the mean. Oh, sorry. It's the average of that. Cool. And our Y bar is the average of this. Okay, so we have our X bar and our Y bar. And we see the equation here. To get the B1, the slope is just R times this divided by this. So I'm going to put B1 here for our sample. I'm just going to do equals R times, so I did shift 8, parentheses, and then it's oh, sorry, it's not that. It's the standard deviation. My bad. So I need 2 more steps first. So we need the S of Y. We also need the S of X. Nothing too crazy going on here. Okay, so the standard deviation of Y, I could put in equals stdev dot sample for this. Want one too many, that's okay. Okay, and now I need the standard deviation of the next one, so it's equals stdev dot s. I need these. Cool. So to get the B1, right, which we know is our slope of this thing, we should be getting what? 0.1742. So what do I have to do? Equals, and then I have to just put the first term, which is our R, and I have to do times parentheses S of Y, S of Y. Well, let's make sure that's actually Y, and I didn't mess up the order because it looks too big. Yeah, this is S of X. See, I could already tell this was too big of a number. So this is your actual S of X, and this is your S of Y. That's why it's always useful to have everything together so you don't make a mistake. So equals R times parentheses S of Y divided by S of X. And we know we should get 0.1742. Here it is, 0.1742. That's how we can get that value. And then for your y-intercept is the mean minus the slope times the mean. So to get your y-intercept, which we know is just b0, we know it's got to be the equal, so it's going to be the y-mean, the y-bar minus parentheses, whatever we found for b1. Then all I have to do is multiply that by the x-mean, which is here. And to get that, we should get a 10.872 for the other part. Got it. Why is it negative? Because it's going to hit down here below the line, and we've got a minus here. So that's how you get all the parts. But if you just click it, it comes right up for you. Isn't that nice? If you don't have the actual data points, you just have these. These are the formulas to use. All right, let's keep going. Hopefully that was useful. Let's see if they got the same thing, negative 10.87, negative 10.87. And then this one, so they got 0.174, 0.174, exactly the same. Okay. Oh, then they want it manually. We just did this, and we just did this. Perfect. Graph the regression equation of this. Found examples 1 and 2 on the scatter plot. Okay, well, we have it. All right. So let's keep going. We're moving on. This helps us to make predictions. What does that mean? If I have a random jackpot number, I should be able to tell how many were sold. And I'll actually write this as B0 because that's the one that they want this. They want this to be beta 0. Either one's the same thing. If they're predicting a value given a specific value, we should consider the following. The regression does not appear to be useful. Don't use it. A good model. If the scatter plot best fit looks. Okay. Let's actually see if this is significant since we did all that extra work. Yes, it's very significant. So we know it's a good model. Remember, this is what we're looking at. Okay, and we still have to understand what this residual means, but at least we know our p-value, it looks good for the jackpot. So let's go further along and really understand what that word residual means. If it's too far away. So extrapolation is like if, let's say, we had a jackpot of like a really large number, right? If it was like over here, like 700, or if it was like over here, like 2 million instead of like 150 million, right? If it's all the way down here, we're extrapolating. We're not sure if it's good enough. Okay. The regression graphs the shadow plot. It's linear. It's not much beyond the scope. Yes, it's a good idea. No, it's a bad idea. Okay. Making predictions, use the jackpot titles. When the jackpot is 625 million. Okay, so how do we do it? So if it's 625 million, remember we have this equation. So if I have y, our prediction for y equals what? B0, our intercept, plus B1x. Well, we have all the pieces. So they're telling us our x is 625 million now. We found out our B1. Our B1 is 0.174. And we know this is going to be a negative 10.872. This is going to give us exactly what we need, okay, to figure out. So if the jackpot's this high, what should it be? Even though we're extrapolating right now, let's see how close it is. So I'm just going to pull up a calculator to just show you how I would do it. So I do 0.174 times 625. So I got 108.75 tickets sold. And then I have to subtract 10.872 for the intercept. So we're going to get a 97.878. Does that make sense? Yeah, we're over here. It should be somewhere up here around 90s, close to 100. Ta-da. All right, let's keep going. There it is, 97.9 million tickets sold. 97.9. Okay. Your turn, do cars. I'm not going to do that. Okay, so beyond the basics of regression. All right. Interpreting regression equation marginal change. And working with two variables related by a regression equation, the marginal change in a variable is the amount that changes when the other variable changes by exactly 1 unit, the slope. So here basically means for every million added on, for every 1 unit more, it's going to go up what? 0.174. So that's what it tells us. The jackpot by $1 million will increase by 0.174 million. Yeah, exactly what I said. That's what it means by marginal change. All right, let's keep this going. The outlier is the one far away. You can throw these out of your data too. If you see something really messing with your data that's so far away that you think it was just an anomaly, throw it out. It's going to mess with your model. Paired sample data may include influential points strongly affecting it, but still part of it. This is where judgment calls come in, and you have to like use your thoughts to understand an influential point or something that's not so dramatic that helps us. So if we have this data, we have the 0.12, 980, 12, like how does it change things? So I'm not, see, look, but this 1 point really messes with it. I'd probably throw that out, right? I'd throw this one out. All right, we finally made its residuals. This is the important part. So here we go. We stated the regression line represents the straight line that best fits the data, the criterion determined that is better than all others based on vertical distances, such as residuals. The residual is that difference. What do I mean by that? It's the difference between the observed sample of Y and the predicted one of Y. You can think about residuals as errors. So basically, it's whatever we get. So our residual is basically going to be the actual Y minus your predicted Y. Okay, so you ready? You go back to this little sketch that I made at the very beginning. This distance, these distances are the residual. All these little distances, these are the residual. It's basically our errors for whatever line we created. And they draw a nice picture too. So far, the definition hasn't won. Okay, so it's just like the margin of error we have between them. And that's what I think residual is. If the equation was something so simple as 1 plus x, we can see the mistakes here. It's usually never that simple. All right. So the regression equation represents the line that best fits the data according to the least squares property. Okay, so a straight line satisfies the least squares property if the sum of the squares of which is small. So that is what we are doing. Get this line, we're getting the smallest possible sum of all of these. That's what generates the line. That's how it builds this line. That's why it's called like residual line, because we're trying to get, or the line of least squares, just we're getting the smallest possible sum of these values. That helps us really understand it. So if you were to take this equation, I might as well show you this one too, because I think this is important to like really understand what's happening here. So here we go. 8, 12, 20, and 24. Then we got 4, 24, 8, and 32. So this is our scatter plot. Right away, we have our little scatter plot. So we can drop it in. Oh, I didn't have them highlighted first. So we have our scatter plot. Ta-da! And then we can add the line. There's our trend line. And I just always like putting the equations on it. So I know exactly what's happening. Perfect. See, 1 plus x, 0.355. Now we have all of these residual differences. So if I actually go to data analysis, and we go to regression, and x, sorry, we always do your prediction first. Here's the y. Sorry, that's the x, the other one's the y. I have the residuals. Now, if I click OK on this thing, notice it comes up on a new one. So here's the residual plots. It's showing you how different they are from each of them. But basically, we know that our residuals here, they give us a sum of square and means they give us all these values for us. We've got our r squared. It's not significant, so we probably wouldn't use this for much. Okay, but let's look more into the residuals. How do we get those differences? How do they get these differences? They're subtracting every y value. They subtract every y value from the ones that we had. So if you look at our equation, this is actually giving you it, but if you look back at the equation, it's like, okay, what point is this, right? Like, how far is that? How far is this? We can label these points if we want, we can put on data labels if we want. But I want it for all of them, so. We can see exactly where each of these points are, because we only care about the what. We only really care about the y values of these points, then we can see how far they are away from the line. This is what gives it the residuals. It shows us exactly what they are. You can do them one by one, but it's kind of annoying. So we square all these differences. We get our value of 364. And if we look at our Excel, you can see it should be the same thing. Residuals, it says 292. So I'll actually have to see exactly where they get it from. But let's keep looking. Fortunately, we do not need to deal with these properties to find the equation, the regression line, blah, blah, blah. So we can use calculus to help us out using derivations. I can explain what that is if you'd like, but let's see if we can get the actual plots, because that's something that comes up. We notice we should begin with a scatter plot, verify the pattern is a straight line. A residual plot can be another helpful tool in analyzing the correlation and the regression. So the residual plot is a scatter plot of xy where each y coordinate has been replaced by the residual value. So it's y minus y. Thus, it's x. So this plot, the residual plot, is our x terms, but it also gives you the residual within it. So this is our x. And our first residual is this value. So we can actually get all the residual values by just putting on the labels. This one squared, this one, this one. I think we multiply them all. But there's our residual plot. Oh, here they all are. Here are residuals. Why do I only have 3 instead of 4? Did I do one less in the picture? I might have done one less in the picture. Oh, because I had labels on. That's why I didn't have the full value. Oh, I'm so sorry. So sweet. Let's do it again to get the actual value. So this was my mistake. Guess what? We all make mistakes. I knew it would come out when I started doing the math. So we're going to go to data analysis here as soon as it wants to turn on. So I can go to data analysis. I can go to regression. Now you see how I have labels. Boom. Now it's the full thing because I was acting like line 1, row 1 was just a label. We all make mistakes, right? Here we go. Here's the 4 lines. We've got everything here. Here's the 364 residual we wanted. Here are the values that we need for each. We can turn them on. And we have the residuals right here, -5, 11, 13, and 7. And then how do we make that into 364? I'm pretty sure we square them and we add them. I'm going to double check that. I'm pretty sure it's a square and an add. It is a square and an add. So ready? Here we go. So here we go. Equals, we got to square and add them just to get the value. So equals this one times itself. Boom. And then if I do a draggy down, I get them all. Nice. Now all I have to do, oops. All I have to do is sum them. So I'm just going to hit the sum button, go to home. Oh, well, there's a bunch of stuff above it. So equals sum. Here we go. We should get the 364. Yeah, cool. Obviously, this stuff is a little confusing. I mess it up myself. So hopefully this is getting clear. And that's what the visual plot is. Awesome. Okay, we're ready for the questions. I hope you're excited. But here is, did I really lose it? There, it's the residual plots. Here's all 4 points. You can see, if you want to, you can add them on by putting a label on them. But honestly, you can see it. Look, -5, 11. What was this one? I can't see it. And then we have 17. I guess that's at 13. I can just barely, oh, because that's over the 20. So if I stretch it out, you'll be able to see the difference. No, I gotta move this one too. There we go. These are the residuals. Ta-da. Square and we get the line. It's basically just how off they are from the actual points, because not everything's perfect. So here we go. We're ready for the questions. I hope this one was useful. But we got 1, 4, 10, 16, and 17. 1, 4, 10, 16, and 17. We're starting with number 1. All right. Using weights and highway fuel consumption of the 48 cars listed in this data set in appendix B, we get this equation where X represents weight. What does Y represent? So what is the Y? So we know Y. So for A, we know this is the predicted outcome. So what are we trying to predict? So X is the weight, Y is the fuel consumption. Predicted based on the weight. Let's go to B. What specific values of the slope and the y-intercept? Okay, so the slope is always the one in front of the x, so we know our slope, which we know is b1 in this case, -0.00749, and then we should go 3 significant figures, so it's -0.007. That's the way they want it. Boom. All right, and let's go to B0, which is our y-intercept. And what is our y-intercept? It's actually a positive value, 58.9. Nice. So we got ours. We have it started. Let's go to C. What is the predictor variable? The predictor is your x. It's the weight of the cars. And what is D? Assuming there's a significant linear correlation between weight and highway fuel consumption, what is the best predicted value? Okay, so we have the equation. We just put it in. So This is what we're looking for. 58.9 minus 0.00749. When they say significant figures, I believe they mean values or numbers. So I'm actually going to put the 49 here as well. All right. And then we're just got to multiply this by Rx, which they say the car weighs 3,000 pounds. That's a big car. Actually, my truck's kind of the same. So here we go. 3,000 times 0.00749, and I'm just going to make that negative. And all I have to do is add the 58.9. I guess I wrote the wrong thing, so it's time to do it again. We should not get a negative weight. So 3,000 times 0.00749, and we know this is negative. And I'm going to add 58.9, and we know it's 36.43. That's our fuel consumption, assuming it's per miles per gallon. Ta-da! So here's number one, nice and easy. Let's get to 4. Numero quattro. What is the relationship between the linear coefficient and the slope of the B1 regression line? That's a really good question. So we know this is a slope and this is a regression line. So what is the relationship? They kind of mimic each other, right? So if we know R is that crazy formula, right? But we know the slope comes from that one. Remember, so B1 is just going to be R. I believe it is the SY over the SX. Just double check. Nice. Yeah, so that's where our slope comes from. The R builds our slope. How are they related? Correlational coefficient. If you want me to do the derivatives, do the calculus of this, just shoot me an email. I don't want to overload you. So correlation coefficient builds the slope using this. So this is this value, and the slope is, so they're very connected. That's the relationship. One builds the other. You can think of this as the predictor line. And what does this have? So what does this slope have that this doesn't? This includes, it's basically including the residuals. You can think about that, sorry, that this one includes the residuals. And this one is kind of separate. So this is including the residuals, they'll find it. All right, so let's go to the next one, which is 10. Here's 10. Find the equation, the regression line, examine the scatter plot. Okay, so I've done it twice with that. I might as well do one on scatter plot, and then I'll leave the last one for you. So here's 10. I'm going to do this on, I'm always trying to show you with both. So we go here, go to StatCrunch. Here's our StatCrunch. Let's see if I don't have to open it this way. Come on, work for me. Sweet, it worked for me. I love it. I love it when I don't have to do extra stuff. So we know, got our StatCrunch here. And this will be the last one I do for this video. I hope it was helpful. It's just X and Y. All right, whenever you want, X, Y. All right, so we have 10. Oh, sorry, it's the bottom one. So 10, 8, 13, 9, 11, 14, 6, 4, 12, 7, 5. Is it 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It is 11. Okay. 7.44. Sorry. 7.46. 6.77. 12.74. 7.11. 7.81. 8.84. 6.08. 5.39, 8.15, 6.42, 5.73. All right, so what do we have to do? All we have to do is go to stat and we want to do regression. We're doing a simple linear regression because it's just two things. The x value is x, the y variable is y, hypothesis testing. So they don't give us this. They don't give us one way or the other. We're just going to assume that they're not equal. This is if you want to put a direction on it for your alternative hypothesis. Your confidence interval, we can leave it at 0.95 if we want. We can have the hypothesis test. Either way is going to be fine. Fitted line plot. Let's also get one of these. Let's also do a residual index plot just for fun. Yeah, let's do some more of these just for the fun. All right, let's see what we got. Compute this thing. All right. They wanted what? So here's our line. Ta-da, here's our regression line. This is the one data point that's off. It's making it higher, right? You see how it like changes the slope? I'd probably throw this one out, whatever this, what is this, 13 and then 12. Yeah, this one just seems off. I'd probably throw it out of the data, which is fine. But they wanted the equation of the regression line. So y equals 3.00024549 plus 0.449. We just need 3. So it's 3.00 and 4.99. That's all we really need. See, there's the 3.00. There's the 4.99. Examine the scatter plot and identify a characteristic that is ignored by the regression line. Well, this was not really ignored, but it's kind of pulling it away. So this would be the scatter plot piece that I feel like I would throw out. We've got all the residual ones, which is cool. I like it. These are the residuals. See that one point that's off. That's the y's versus the one residual point, and the predicted values versus the residual. So if we were to do the same exact thing, and we were to just get rid of this point, let's say we just did not want this point, we can look at this again. I think everything else should be the same for when I did it. Oh no. Just hitting control and click. Cool. Notice now it's significant. The values are significant. This value is different. Our correlation coefficient just looks like a much better graph, and we know we've got a significant value here. Ta-da! Look, they're all in line. They all look pretty. The residuals are smaller. Everything looks nice. Nothing seems super far away now. Everything kind of looks the same, which is really cool. So hopefully that made sense for everybody. I hope this was a good video. If I confuse you at all throughout the whole thing, sorry about that. I'm just trying my best. Feel free to reach out for questions and enjoy your day.